In the last module, we had looked at various mechanisms for heat transfer. So, we had looked at the fundamental mechanisms: conduction, convection and radiation. We also looked at the basic governing equation for conduction, convection and radiation, and we also saw a couple of examples for each of these modes of heat transfer using the basic formulae that were seen in the introduction slides. So, to summarize that, we just have one slide, which was the last slide in the previous module. So, conduction essentially is because of diffusion of energy due to random molecular motion, and the governing rate equation is Q double prime. The subscript x means it is in the x direction, K is the thermal conductivity, with this is in terms of heat flux watt per meter square. So, minus K dt by dx. Q double prime for convection is H into Ts minus T infinity, and we said convection is nothing but diffusion of energy due to the random molecular motion and bulk motion. So, it is conduction plus bulk motion of the fluid, and radiation of course is energy transfer by electromagnetic waves. Rate equation for radiation from a given surface is sigma epsilon Ts to the power 4. Sigma is the Stephen's constant, epsilon is called as the emissivity, which is the property of a surface which is between 0 and 1, and for a black surface or a black body, emissive power or E would be Eb, which is sigma Ts to the power 4. So, essentially E is equal to epsilon into Eb, because this second and third term, that is sigma Ts to the power 4, is nothing but the emissive power of a black body which is at temperature Ts. Okay, so, this was the basic, and we also understood that when you have pure natural convection, radiation cannot be neglected. We saw a numerical example where radiation contributed to about 40% of the heat transfer, total heat transfer, even though the temperature difference between the for the heat transfer was around 10 degrees centigrade. So, the air around the human body was at 27, the human body was at 37, the temperature difference was 10, but radiation contributed about 40%. So, this is something which we need to remember. It is not something which is intuitive. So, in natural convection the heat transfer rates are low, so radiation also is very important. Okay. Now, we go on to the next set of fundamentals which are very important. This is essentially your conservation of energy. See, conservation of energy, conservation of momentum, all these things come in various courses. Okay. So, first law essentially is your conservation of energy, but it is in a form which is useful in thermodynamics, but in the broad sense it is the same conservation of energy that you are seeing here: energy coming in, energy going out, energy generated, energy stored. For example, this is a very pertinent simple example: E dot in minus E dot out plus E dot generated is equal to E dot stored. This is your energy rate basis equation. So, every term is in watts or joules per second, and this is energy coming in. So, if I have a random control volume, this is my control volume, energy coming in, the rate at which it is coming in, the rate at which energy is going out, the rate at which energy is generated within the control volume, and the change in energy with respect to time is the dE by EST, or which is dE by dt. dECV by dt. This is what was the term on the left hand side of your first law of thermodynamics, dECV by dt, rate at which energy is changing inside the control volume. So, what is so important about this equation? It is the basis for most analysis, including non-engineering. For example, if you take your bank account, money coming in through your salary is nothing but your E in. So, money in, it could be in various forms: salary, it could be a lottery, whatever. Money out is by various forms. You have bills, EMI, You have many ways money can go out, rent, whatever. That is money out. What is this energy generated? Interest, which is the bank is giving you. At the end of the month, if this plus this is greater than this, you have a positive change. So, you started off with 1000 rupees coming in, 800 went out, and 20 was your interest. You have 220 rupees more at the end of the month, and that is essentially what is your saving. So, your energy balance or energy transfer is nothing but a budget of what is happening with respect to energy in a control volume. So, this is something we would want you to remember. E dot in minus E dot out plus E dot generated equal to E dot stored. So, if you put that in words, it is written here, amount of thermal or mechanical energy entering the control volume minus amount of thermal or mechanical energy leaving the control volume, which is E dot out, plus the amount of thermal energy generated within the control volume, E dot G, is nothing but it is equal to energy rate of increase in the amount of energy stored in the control volume, which is the E dot stored term. If I integrate this with respect to time, these are rate equations. If I integrate this with respect to time, I would get total energy in minus total energy out plus total energy generated is equal to total energy change in the control volume or delta ECV. So, this is in terms of joules and the other one is in terms of watts. E dot in both mean the same, both are the same equation, except that one is in terms of rate equation, other is in terms of total energy equation. Very, very important, and it forms the fundamental basis for most derivations, because if I am able to put values or phenomena for all these, it is just a budget of energy that is going to be needed to be done. Okay. So, something which every student, all of you must know at the end of this module is this equation. Okay. So, this is a generic control volume. E dot in could be in by any mode, conduction, convection, radiation. Now, imagine this this one to be your turbine in your thermodynamic analysis. We would just say energy lost by because of poor insulation, the turbine loses some amount of energy. It would not be told whether it is convection, conduction or radiation. So, that is the difference between thermo and heat transfer. So, inflow and outflow terms happen across the control surface. The boundary of the control volume is called as a control surface, and energy has to cross. That is transferred because of mass which is going to come in. Okay. So, I do not if you remember your fluid mechanics, you had what we called as Reynolds transport theorem in fluid mechanics. If you have not studied it, it is okay, you will see it in convection also. There is this is your Reynolds transport theorem. This is a extensive property B, and this is the corresponding intensive property small b, and this is rho. This is your RTT, Reynolds transport theorem. I will just clean this up a little bit. Rho B V dot n cap dA. This is essentially mass flow term, rho into V dot n cap dA, rho AV, which is the mass flow, transport of this property B. This property is what is being transported across the boundary of the control surface. Okay. So, if this is mass flow in, mass flow out, this is integral over the control surface, net transfer of property B. That is what is seen here. That is what is seen here. You have property, whatever property, here it is energy, energy is being transported across the control surface. You have energy coming in, energy going out, and you have energy generated and stored terms, which are volumetric phenomena. How much energy is generated? How much energy is stored? The storage is essentially dependent on the mass. Rho into V is the mass, generation is also dependent on the mass. So, this would be chemical reaction, chemical energy, electrical, nuclear, all those things are energy generation terms. The energy storage term is also having a sensible or a latent component. This would be internal potential or nuclear energy, whatever you may call it, but again this is a volumetric phenomenon. Okay. So, how do you apply these laws? So, first thing is you need to select the control volume, very important. As in thermodynamics, you have to clearly identify the control volume. Appropriate time basis must be chosen, that means over what time interval you are carrying out the analysis. You need to be able to identify all the energy transfer processes that are going to happen and then put it in the conservation equation. You would be able to solve any of these problems. Okay, so sounds very simple, but by the end of couple of weeks you would be able to do it for conduction, when convection also, when the basic formula is given to you. Okay. So, this of course was an introduction slide we saw much earlier. Don't want to spend time on it. We will take a small numerical problem where this whole E dot in minus E dot out business is put. So, you have a 2 meter long 0.3 centimeter diameter electrical wire extends across the room at 15 degrees centigrade as given in a schematic. So, you have a electrical wire which is 2 meters long and 0.3 centimeter in diameter. The room is at 15 degrees centigrade, the air in the room. Heat is generated in the wire as a result of resistance heating, that means I squared R heating. The surface temperature of the wire is measured to be 152 degrees centigrade at steady state operation. The voltage drop and the electric current through the wire are given as 60 volt and 1.5 ampere respectively. Disregarding any heat transfer by radiation, determine the convective heat transfer between the outer surface of the wire and the air in the room. Okay. So, we have the wire dimensions, the room temperature, everything which is known. So, if I just take a look at the schematic, this is the wire which is shown by the red here. You have potential difference of 60 volt, current flowing is 1.5 amperes. So, you know the amount of heat that is generated, I squared R or V into I. V is known, I is known. 60 times 1.5 is 150 watt. Okay. Surface temperature 152 degrees centigrade and T infinity, which is the surrounding air temperature, is 15 degrees centigrade. You are asked to find H. H is not given to you, you are asked to find H here. So, what are we saying? It is a steady state operation, meaning the current, the process has been on for such a long time that 60 volt potential difference is maintained, the surface is at 152, whatever heat is generated is being taken out, and you want the temperature to be maintained at 152. If that heat is not taken out, the surface temperature would increase. If more amount of energy is taken out, the surface temperature would decrease. We are not looking at those kind of situations. We are looking at a situation where whatever heat is generated in the wire because of this passing of electric current is completely removed and the surface is maintained at 152. That is what is called a steady state operation. Okay. So, we are neglecting radiation heat transfer, not a very good assumption, but the problem asks you to do. So, you can do that, and if you go back, go to the analysis, Q is nothing but energy generated, which is V into I. We said it is 90 watt, I think I said 150 watt, sorry about that, 90 watt. The surface area, which is nothing but the area of the wire, which is pi into D into L. The dimensions are given to you, length is given 2 meters long and 0.3 centimeter diameter, converted it to meters, 0.3 into 10 to the power minus 2 into 2 meters long, you have the area. From Newton's law of cooling, Q is equal to H A Ts minus T infinity. So, all the numbers are known, you can find out H, which is about 35 watt per meter squared Kelvin. This, please remember, is what is called as an average heat transfer coefficient. What is average? Meaning you do not worry about temperature at every point on the surface. The temperature may have varied along the length of the wire over 2 meters, but we said the entire wire is at 152 degrees centigrade, and therefore, this is called as an average heat transfer coefficient. This is a simple setup. Okay. Many times it is done to have an idea of the H value, and radiation can be eliminated by keeping the surrounding surfaces at the temperature of the wire. Suppose the entire room, everything is at 152 degrees centigrade, then radiation can be completely ignored, but here it is not a very good thing to do so. Okay. Okay, this is another simple numerical problem which illustrates the rate of energy transport phenomena. Hot combustion gases inside a furnace are separated from the ambient air and its surroundings, which are at 25 degree, by a brick wall 0.15 meter thick. So, this is a combustion chamber which is having combustion gases. You have a brick wall and this is the outside. What you see here is the outside. Okay, the outside surrounding temperature is 25 degrees centigrade. Under steady state condition, the outer surface temperature is 100 degree. That means this surface is maintained at 100. They want this surface to not go beyond 100. Free convection to air and adjoining surface is characterized by convective coefficient giving 20 watt per meter squared Kelvin. That is also given to you. Your ambient air is at 25 degree. Same thing here. The T infinity or whatever is said is 25 degree. So, we will just come back to this picture. You have the thickness of the brick wall given to you. You have the thermal conductivity of the brick wall which is given to you. You have combustion gases which are providing the heat. We are not worried about what that is, but on the outside you have convection. So, let us just illustrate this nicely for us. So, typically if this is the wall and this is your combustion gases, combustion chamber, this is going to be at a very high temperature. T is very high. Let me call this T infinity 2. This is T surface 1, T surface 2, and outside is T infinity, we will call this. Typically, to show convection, we have this kind of a symbolic representation, H comma T infinity with either upward or downward arrow. Books will put this kind of cloud. This means there is convection. Okay. Here also there is convection, H comma T infinity 2, but we are not bothered about it. We are saying the heat is coming in here. There is the brick wall and there is convection from here. The thermal conductivity of this brick wall is given to you and the thickness of the brick wall is also known. So, thickness is also known to us. Okay. So, we are asked to find a few things. This schematic I drew to show you that H comma T infinity is typically represented this way, indicating convection. Okay, we are asked to find the wall inner surface temperature. We are also given in the numerical problem, this surface is at 100 degrees centigrade. So, Ts2 is known, H is known, T infinity is known, okay, K of brick is known, T of brick is known, thickness of the brick is also known. Area is not known. The area is what? This is the area of the wall. We do not know that. Okay, we do not know the surface area, but we will see that surface area does not matter because here also convection is the area phenomena, the areas will cancel off. What are we trying to find out? We want to find out the temperature on this wall temperature we have to find out, inner surface. So, it is essentially, if I want to draw this, conduction from this brick wall through this brick wall and convection to the outside. So, if I do the analysis for this control volume, which is the right hand side wall, heat coming in, Q conduction from the left side is Q convection to the outside. So, for the control volume shown by this one, E dot in, this is E dot out. We write our equation E dot in minus E dot out plus E dot generated is equal to E dot stored. We are talking of steady state. This E dot stored is E dE by dt. This is 0 at steady state. In this control volume which is shown here, we do not have any energy generation because it is a control volume which is just a surface. So, there is no energy generation. So, this is 0. We have simply E dot in is equal to E dot out. How is heat coming in? this is the surface of the brick wall. There is an inner surface, there is an outer surface. So, through this energy is coming from Ts1 to surface S2 by conduction. So, the mechanism is conduction here, energy is going out by convection. So, E dot in is equal to minus Kas dt by dx. So, we have thermal conductivity, we do not have the area, dt by dx we know, temperature difference is what we need to find. So, I will write minus k, I will not use much of my mind, I will just go with the coordinate system. So, this is the coordinate system x, Ts1 is unknown, Ts2 is known 100 degrees centigrade. We know that this is going to be higher than 100. So, Ts1 minus 100 divided by x2, which is the thickness, minus x1. What is x2? That is a 0 plus the thickness. I forgot the thickness. Let me go. The thickness is 0.15 meters. So, this is 0.15 minus Kas Ts1 minus 100 divided by 0.15 minus 0. This is your E dot in. I have not used any of my brain or anything. I have just used Fourier's law, kept the minus sign and went Ts2 minus Ts1 divided by x2 minus x1. Okay. So, dt by dx will be negative, the minus sign needs to be there to take care of it. E dot out is by convection H into surface area Ts2 minus T infinity. So, I equate these two, I would write minus K, what is the K for the brick? K for the brick wall is given to me as 1.2 watt per meter Kelvin. So, minus K is minus 1.2 into As into Ts1 minus 100 divided by 0.15 is equal to H, which is known, As again, which is 100 minus 25. H was given to me in this problem as 20 watt per meter squared Kelvin, and As cancels off, and from this you can calculate your Ts1, which is nothing but 287.5. I calculated the Q separately and then equated. Here they have done it the same way, it is exactly the same thing. The brick inside surface temperature is 287 degrees centigrade. We had one dimensional conduction assumption, we had radiation being neglected, we assumed steady state, we also assumed constant thermal conductivity of the brick. It was given to me, so it is assumed. And we also, without saying, H was also given to be uniform, which is one assumption, because in real life H would actually vary along the wall, but that we have not worried about at this case. Okay. So, what are we trying, where are we going with all this? Now, we are going to start focusing on steady state conduction. Conduction essentially is what we said, molecular transport of energy and of heat, and we want to see how 1D conduction, that is conduction which is dependent only which is only going to be in a single direction, either x or y or z, or in case of radial system along the radial direction, how to solve, how to formulate the problems, how to solve for temperature distribution. Why? Because in heat transfer it is important that we get the temperature of the region or location of interest. Okay. So, that is what this slide essentially says. We have heat transfer which is having a direction and magnitude. We know that because heat flows from high temperature to low temperature, that means it is having a direction. It also has a magnitude, of course, the number that you get by calculation is the magnitude. The rate of heat conduction is proportional to the temperature gradient, we saw that. So, Q is directly proportional to delta T. Heat conduction in a medium in general is 3-dimensional and time dependent. T is a function of x, y, z and t. When we are talking of time independent situation, we call it steady state conduction. When temperature is varying with respect to time, we call it unsteady or transient conduction. So, first we will go through steady state, later towards the end of conduction we will go to unsteady state. Okay, so this is just presented here. t is a function of x, y, z, t in general. 1D in x, we could have t as a function of x alone or y alone or z alone. Steady state, of course, if it is function of 2 dimensions, x, y, y, z or x, z, 3 dimensional, it could be a function of all the 3. So, all this is the general one. So, what is written here is general. What we have shown here is steady state 1D, steady state 2D, steady state 3D. That means, you are not having anything as a function of time. Temperature is only a function of space, x, y or z, x and y, y and z or x and z. This is 3D. 3D steady, 2D steady, 1D steady, general. Okay. So, we can have now a simple case of a cylindrical rod with lateral insulation. That means, insulation is there around the circumference. So, heat is only going to flow from the left wall to the right wall. So, for example, if I draw this here, I have a cylinder. This could be a, there are multiple things there. You have a cylindrical pipe, and this is the insulation on the wall, and heat will not flow from the circumference. So, if this is the wall, you do not want any Q to flow. So, you will put insulation around it, which is what this problem is. So, heat will flow only from this surface to the corresponding surface on the thickness, at the thickness of T or L or whatever it may be. That is what this problem is showing. So, delta x is the length over which the heat transfer is occurring, and temperatures are T1 and T2. So, cylindrical rod of known material is insulated on its lateral or circumferential surface, ends are maintained at T1 and T2, and you are asked to calculate, you are asked to write down the expressions. So, Q is proportional to A dt by dx, we saw that. So, which is nothing but Ka dt by dx. Typically, you can have heat transfer in the radial direction and no heat transfer in this direction. This is called as the axial direction, this is called as the radial direction, along the radius, along the axis, along the radius. So, if you are having radial conduction, QR would be minus Ka dt by dr, or QR is equal to Ka dt delta T by delta R. Both ways, it is the direction, the key thing here for you to note is that temperature difference in the direction of heat transfer. Divided by thickness in the direction of heat transfer. Thickness or radial delta R, whatever, that is what is the key. Okay. So, applying this, we have seen in the first module itself, Q is nothing but minus Ka dt by dx, and heat flux is minus K dt by dx. So, we have seen this. In general, if we write heat flux is minus K into del T, del if you expand, you have I dt by dx plus J dt by dy plus K dt by dz, and typically heat flux in the x direction, y and z direction are given. Typically, we think of medium to be isotropic, which means we do not have anything which is varying in the spatial direction. So, thermal conductivity is independent of the coordinate direction. We call it an isotropic medium, which is what our analysis in this course is going to be most of the time. Unless specified, we will be dealing with an isotropic medium. Now, thermal conductivity is how fast heat will flow, and how fast heat will flow means the body would be a good conductor. If it is slow, it will be called as a poor conductor. Wood is typically a poor conductor. That is why your handle for several cooking utensils would be made of wood. Okay, a pan or something would have a wooden handle, or a plastic with some kind of a plastic which does not degrade with heat, that kind of a handle would be there. Metals, for example, would have copper bottom vessel, you would have seen. Thermal conductivity is very, very high. Copper is about 400. You will have aluminum vessels, stainless steel vessels. You seldom will have wooden vessel in which you will be cooking. Okay, so, thermal conductivity is very material dependent. Typical values that you see, something which you should kind of remember. I am not saying you need to by heart this, but metals will have of the order of hundreds. Water is about 0.6, air is about 0.026. 026, 0.6, copper is about 400, aluminum is around 200, stainless steel is around 15. This is a graph which shows how thermal conductivity varies. Gases are here, liquids are somewhere here, solids are somewhere here, and you are talking of pure metals which are in the range 100 to 1000. Alloys would have slightly lower. Non-metallic solids would be in this 1 to 10 or slightly little bit more than 10 range. Okay, so in the next module what we will do is we will look at how thermal conductivity is affected. You have both the electronic component and the lattice component. We will spend about 5 minutes on these things and also how and define a property called as thermal diffusivity, which is very important, which is essentially how fast the body transfers heat by conduction to how much it stores energy in the form of heat. So, we will define that property alpha, and after that we will go to the 3-dimensional heat diffusion equation in Cartesian coordinates, that is x, y, z coordinates. That is something we will carry out in the next module. Thank you.